So in this video, we'll look at the integration of irrational functions. So in case you don't know what is the rational function, and please look at the current problem here. We try to integrate a fraction where the denominator and the numerator are both some polynomials in variable x. And please look at the purple color here. Degree of p is actually the highest power of the polynomial of p. And I claim that to solve such a problem in integrations, we have to follow some steps. And the first step is that we have to check out the degrees of top and bottom. And the case A is the case where the bottom, the denominator, actually has a higher degree than the numerator, and case B contains the remaining cases. And I claim that to solve case A is slightly easier, and case B is not that difficult, but there's some extra steps that we need to carry out. And for now, let's focus on the case where the denominator has a high degree. We need to split it into a few cases, but before that, let me state it here. So for the case A where the denominator Q has a higher degree than the top, you have to factorize the denominator completely. For example, we can check it out. If I give you a polynomial in the denominator, which is x squared minus 9, and I believe that you're able to factorize it because there are two roots, which are 3 and minus 3 for this problem. So the factorization is really the same as x minus 3 times x plus 3, right? And or the other case, for example, you can look at maybe x cubed plus 4x. And I think this case is quite easy in the sense that you can take out the x as a common factor from both terms, and the items inside the bracket is gonna be x squared plus 4, right? And please note that this one cannot be factorized further. Please ask yourself why, because when you try to solve this problem, there's no real solution for x. For those of you who are very good at using calculator all the time about this kind of problems, if you use calculator, you would notice that you're getting solutions like 2i and minus 2i. When you see the solutions like 2i minus 2i, I is not real number. This one is called imaginary number actually, so they are not the real solutions we look at. Anyway, it gives you a sense that it cannot be factorized. It means that you see, this factor, we call it a degree 2 factor, in the sense that after you completely factorize this polynomial, which is degree 3 itself, it has one degree 1 factor, right? And it has a second factor which has degree 2, which cannot be split further. For example, like first case, this polynomial itself has degree 2. But we cannot say the fact it has only one factor of degree 2, right? Because you can actually factorize it further to have a complete factorizations where both factors are degree 1, right? So I'm looking for complete factorizations. And let's look at one more example. For example, you can look at this case like x cubed minus 5x squared plus 6x. And for those of you who are good at this, we can pick out the common factor x first. So we're having a degree 2 polynomial inside. And this one is not a degree 2 factor because you can further split it. I think the factors you have for the things inside the bracket is actually the same as x minus 2 times x minus 3. And you see this case means what? This case means for a degree 3 polynomial now, you actually have 3 degree 1 factors, right? And this is really the first step. This is really the first step. Whenever you have a integration of rational functions and the denominator now has a higher degree than the top, which is the numerator, you have to factorize the bottom first. And after this process, you can deal with the remaining steps. So let's say now after the process of factorization of the denominator, let's look at the factors that you have. If all the factors are degree 1, and all the factors are different. I put it in the category 1. It belongs to the easier case, but just to make sure you understand what I mean by all factors have degree 1 and they are different, let's look at the current example now. You see, for example, like this case, if after factorization you're having this one, you see this polynomial actually has degree 3 because you have the highest power term, which is x times x times x. And this case has 3 degree 1 factor. And all of them are different, right? So all of them are different. So this case belongs to the case 1. And how about this case? if you have something like this one, you see, this one does not belong to the category 1 because of the fact that you have two factors, they are the same. They are the same, which is x minus 2 and x minus 2, they are the same thing, right? So it doesn't belong to our current case. Or you can look at another case when you have something like this. This one also does not belong to the category 1 because it actually has x squared plus 9, which cannot be factorized further. So this one is actually a degree 2 factor, right? And you have to identify all the cases. I'm just talking about in category 1, the case where you need to have all factors degree 1 and all of them are different. I'm just talking about that. And let's see how to solve this. So for example, let's look at this case. Now the bottom, which is the denominator, is factorized already. Both factors are different and both of them are degree 1. And on top of that, you see the numerator actually has degree 1, the numerator. But the denominator actually has degree because the highest power term is x times x, which is x squared. So you see, it belongs to our current case A where the denominator has higher degree than the numerator. And also, you have done the complete factorizations. Both factors are degree 1, and they are different. So it belongs to our current category 1. And I claim that in this case, you can use the partial fraction method. Partial fraction means what? Partial fraction means you can split such a big fraction into some smaller pieces of fraction depending on what factors you have. In the current case where you have two factors, I claim that I can actually split it into a smaller fractions based on the factors you have. And at the top of the fractions, you have to put a constant there. And this process is actually called partial fractions decompositions. Once you have a partial fraction decomposition, you have to try to find the AB in the next step by some algebras. And the easiest way to do is we can make a common denominator on both ends, because once you have the common denominator, we can just compare what you have at the top in the numerator, right? Now you see, for the first term, A, it currently has the x minus 2 at its bottom, the denominator already. So if you make a common denominator, you have to multiply A to the factor it doesn't have, which is x plus 2. And similarly, B needs to multiply to the factor it doesn't have, which is x minus 2, right? Now you see the bottom of the fractions, they are the same. We can multiply it out and we can just compare the numerators. And from there, we can solve for the A. So you can look at the current case. I'm just comparing what we have in the numerator. And to solve for the A and B, we probably can make some clever choices of x. For example, if I choose x equals 2, I hope you can see what's happening if x is 2. The second term is 0, right? So we don't have to care about the second term. In that case, we can solve for A. So let's see. The left-hand side is 4 times 2 minus 1, which is 7. The right-hand side, this term is 0. And we can solve for A. I think x is 2. So it means 4A is actually 7, and A is actually 7 over 4. So it's done basically for A. And for B, we can use a similar method. I hope you can see what choice of x that you can use such that this term can be made 0. I can actually use x equals minus 2. So now the left-hand side is 4 times minus 2 minus 1 equals, and the first term, which has the A, is already 0 because you see, x plus 2 now is 0 because x we set it to be minus 2, and B times minus 2 minus 2, right? So minus 4b, which is the right hand side, I push it to the left, actually equals minus 9, which means b is actually minus 9 divided by minus 4. So b is actually 9 over 4. Now keep these two values in your mind. We have to go back to the integration problems. So you see the values for the a, which is for the first fraction, which is 7 over 4, and the value of the b, which is for the second fraction, which is 9 over 4. Now, instead of integrating a big fraction like this, which is not that easy, by the partial fraction decomposition, I'm able to split the big fraction into two pieces. So we can do the integration term by term now, and let's do it together. For the constant at the top, I can pull it out. So you need to tell me the integral 1 over x minus 2. And similarly, for the second term, I can pull out the constant out, and you have to let me know the the integral for 1 over x plus 2. And for these two, they are quite easy, simply because of the fact that the denominator is degree 1. So if you quickly use a substitution u equals x minus 2, it will solve for the problem. And anyway, we'll skip the step a little bit. This integral is actually the same as ln of x minus 2. The second integral is going to be ln of x plus 2. And I'm able to do it that quick, mostly because of the denominator, which is degree 1. So it allows us to use, for example, for the first one, you can actually solve it by using the u substitution. U is x minus 2, and du is actually dx. And after using the substitution successfully, you should be able to get what I wrote down here. So it becomes the integral of 1 over u times du, which is ln u, and u is actually x minus 2. Yeah, so that's the reason why we actually have this. And similarly, for the next term, is the same concept. You have to use u equals x plus 2, then you can solve this. So anyway, it gives you a sense that when the degree is actually 1 at the bottom, you can actually integrate it fast. So, but before that, you have to do a partial fraction decomposition first. Maybe you can do one more example. So please look at the current problem. I'm giving you this integral of a rational functions, and please check the degree at the top and the bottom. You see the top has degree 2, and the bottom has degree 3, so it's fine. We can carry out the partial fraction decomposition. Now it is very good because we're in the category 1, which is a case where the bottom actually has all different factors, and each factor has degree 1. So we can do a partial fraction decomposition as follows. Because we have 3 factors, so we can split the big fraction into 3 smaller pieces. And for the degree 1 case, it's actually easy. I'll just put the constant up there. And you need to find the ABC before carrying out the integration. And if we make the common denominator, we should have the following. Please check both fractions at the left and at the right. And I make a common denominator on the right-hand side. And the numerator is somehow a little bit long, but please check the factors that you have. So now please compare the numerator on top of the left-hand side and the top of the right-hand side. And I claim that if you choose some clever values of x, you're able to solve for ABC separately. And otherwise, it is not that easy to find ABC at the same time because you actually have 3 unknowns. And we need to eliminate 2 of them. We try to focus on finding one of them. And I claim that I can choose x equals 0 because you see, 0 is a good choice because this factor is 0, which means the last 2 terms are actually 0 when I choose x be 0, right? So it means I'm having something like this. So when x is 0, what you need to do is something like this. So it means that minus 1 on the left-hand side actually equals minus 2 times a on the right-hand side. So I think a is actually half. And similarly, you can find b and c separately. For example, to find b, I think I can choose x equals minus 2. Please check what's happening. When x is minus 2, it is actually the root of this polynomial, right? It means that when x is minus, the last term is 0, and this term is 0. Because when x is minus 2, this term is actually 0. And it means I can solve for b in this case. So let me write down the next step. So you see, now you can try to solve for it. So the next step is minus 1 equals minus 10 times b. So it means that b is actually 1 over 10. And for the last term, which is c, we can actually check how we can make the first 2 terms 0. For example, we have this factor in the a term and the b term. When we let x be 1 over 2, I think we can make these 2 terms 0 because 1 over 2 is the root for this polynomial, right? So we can solve for c in case. So let me write down the steps. So it should be the current step, and if you solve it carefully, it's gonna be 1 over 5. And from there, we can try to do the integrations. So let me write the next step down. So I corrected a minor mistake here. Please look at the value of the b here. B should be minus 1 over 10 instead of 1 over 10. So I add a negative sign. And please look at our current stage, and you have to integrate the right-hand side after using the partial fraction decompositions. And because all terms have degree 1 in the denominator, we expect the answer to be quite easy. Let's look at it together. For example, for the first term, it's b half, which is the constant of a, and ln x, which is the antiderivative of 1 over x. And the next term, minus 1 over 10, I can pull it out as a constant, and you need to integrate 1 over x plus 2, and it's going to be ln of x plus 2. And the last term, I can pull out the constant plus 1 over 5, and you have to integrate 1 over 2x minus 1. And please be careful here. If you put in ln of 2x minus 1, it's not going to do the job. You have to divide it by 2. I hope you can see the reasoning here. For example, if you try to do it in the opposite direction, where you need to differentiate ln of 2x minus 1, then by the chain rule application, it's going to be 1 over 2x minus 1 as the first factor. The second factor is going to be the derivative of 2x minus 1, right, which is 2. So it gives you a hint that when you try to differentiate just this term, which is ln of 2x minus 1, there's a 2 as a multiplication factor that comes out if you find the derivative, right? And similarly, if you go back to the integration problem, instead of doing multiplication of 2, we have to divide it by 2 to cancel out the effect of the multiplications. And that's the reason why you need to divide by 2 in this case, and that's the end of this video.